Good afternoon, friends. We are continuing our discussion on aircraft dynamic stability. And by now, we are very clear that our approach will be, as I illustrated through mass spring damper system, our approach is identify the equilibrium state, perturbed it, small perturbation, very small perturbation, and then write the equation of motion. So, if you recall, when you wrote the equation mx double dot plus cx dot plus kx equal to f of t, this x of t, these were perturbed variable, that is the distance or displacement from the equilibrium. So, in our sense, this is the perturbed quantity. Okay? So, we wrote the equation of motion in terms of perturbed quantity, and then we try to find out its roots and try to study the behavior of the perturbed quantity x of t, and if it is oscillatory, if it is coming just to the stream without any oscillation. So, we said it corresponds to either oscillatory return under damping case or over damped case or a critical damped case. But the catch point was this x of t is basically measured with respect to the equilibrium, or the another way of understanding is if I disturb it and withdraw it, I say how this motion variable, which is a perturbed quantity, is behaving, and based on that we decide, we say that it is dynamically stable or not, right. Now, we wanted to use this understanding, we wanted to extend this understanding for analyzing aircraft dynamic stability. So, what we did, we said we also will write equations of motion of airplane. In fact, to be more precise, we also know that we have to write perturbed equation of motion for the airplane, because these are perturbed equation of motion. Okay, because these are measured from the equilibrium when the perturbation was introduced. We wanted to develop such equation of motion, which is a perturbed equation of motion for the airplane. But what was our approach? We said initially we will write generic equation of motion of the airplane, then we will introduce perturbation and try to get perturbed equation of motion. And in that approach, we said we will use Newton's laws of motion, and that is external force is equal to mv, rate of change of momentum. Similarly, external applied moment is rate of change of angular momentum. And we all know angular momentum is the moment of the momentum, moment of the linear momentum, to be more precise, r cross mv. We all know this. But what is another point we also noticed here? If I want to implement these laws of motion, Newton's laws of motion, I need to ensure that we are applying with respect to inertial frame. And you know, inertial frame is the frame having no acceleration, right. So, we started developing equations of motion, but not perturbed equation of motion for airplane so far. We are all writing equations of motion, and we found out two important relations, that F equal to m dv, c the center of mass, by dt. Another we got was m moment equal to if I write it correctly, it will be d by dt of hxi plus hy j e and hz k. You could see I am writing E here, subscript E here for unit vector, because we are very much clear and cautious about the fact that if I want to apply this m equal to rate of change of angular momentum, I have to apply it in inertial frame. So, this I, J, and K, they are the unit vectors aligned in the inertial frame of reference. And for our case, earth fixed axis system, has been chosen as inertial frame, although we know Earth is not an inertial frame because it's rotating. But we know since we are doing dynamic stability analysis, which is for a very short period, so we can make this assumption for all simplifications. Not much error will be introduced for dynamic stability analysis. Okay, this is one understanding we had, and we also developed the expression for Hx. Let me write here. I also have requested you, please do yourself these derivations because there may be some sleep from my side. You young men should be able to derive this following my lecture. This is Hx, this is Hy. I say Xx to be more consistent. Iuiz, Sz into minus P Ixz minus Q Iyz plus R Izz. Okay, let me see. Hx is Pix minus Qixy minus Rixz. Hy is minus Pixy plus Qiy minus Riyz. And Sz is minus Pixz minus Qiyz plus Rizz. And we also wrote Ixy is nothing but xy dm. Similarly, Ixz is integral xz dm. And you all know Ixs will be integral y square plus z square dm. These are by definition. So up to this point, we have no issues, but we should not forget when we are deriving all those Hx, Hy, Sz, these are with respect to the inertial frame. That means P, Q, R here are with respect to the inertial frame. Okay? Now, you imagine even this Ix, Iyy, all are with respect to inertial frame. Now, imagine a situation. This is the airplane. Let's say this is your inertial frame. I say Earth, X Earth, Y Earth, and Z Earth. Right? Now, the body will rotate because of its dynamics. So, now what will happen? The moment of inertia of this body with respect to X, Y, Z, E inertial frame of axis will go on changing as the body oscillates, right? So then it is very difficult to, very cumbersome to introduce those things. That means every time you have to compute Ixs for a different instant of time, finding the orientation, etc., etc. This is one. The moment of inertia will go on changing if I am using X, Y, Z Earth frame reference system. That create complication and will become very cumbersome. We are not happy with dealing those. Also, you understand that the forces, aerodynamic forces acting on the airplane depends upon the air relative speed. As I told you last class, if the airplane is stationary on the ground, it will experience no aerodynamic force. The airplane is stationary on the ground, however, wind starts blowing, then it will experience drag force or lift force. So it is the air relative speed that is important, not ground speed. So it is better to work in terms of body frame, right? If I choose a body frame, if I am allowed to operate, knowing very well, body frame is not an inertial frame, so I say X, Y, Z. Let us say body frame means it is fixed with the body. And as the body rotates, this frame also rotates. So one thing is sure, the moment of inertia now will not change about this axis because the axis is also moving. Then also the aerodynamic forces will be proportional to the relative air speed. So along X, Y, Z easily you can compute. But what is the problem? Problem is this is a non-inertial frame because it is a rotating frame. So how do I apply Newton's laws of motion? It says it has to be inertial frame. So if I somehow find out a way to apply this, without violating this understanding that it has to be applied on an inertial frame, and still operate on a rotating frame, my job is done. That means I am asking a question: what is the equivalent way of handling this problem by operating at a rotating frame? Still, this violation will not be there, that it is not an inertial frame. That means, if we are operating in a rotating frame, if I know what sort of a correction I have to add with the rotational frame derived expression, what additional correction I should make, so that equivalently it will become as if I am operating in inertial frame as far as mathematics is concerned, right? If that is true, then let us have a closer look here. So, I give title to make things clear: working in rotating frame. Frame or body frame. Right? So now our approach is very simple. I want to operate in a rotating frame. I know Newton's law, if I want to apply, it has to be in a non-rotating, non-accelerating frame. So I say I will operate in a rotating frame because I have two distinct advantages, and tell me what correction I have to make, add to this result mathematically, so that it is equivalently as if I am working in a non-rotating frame or inertial frame, right? See here, mathematically, if I see external force causing acceleration, mathematically I need a derivative, dv by dt. Similarly here also, m, you see it is a question of dh by dt, that is derivative of a vector. If I want to do a derivative of a vector in inertial frame, suppose this is your inertial frame, xe, ye, ze, let's say v equal to ui plus vj earth plus wk earth. It's a v star. So if I do dv star by dt, I see one is du by dt into ie, second term is u into die by dt. Similarly, other term will come. But if I am working in inertial frame as it is here, die by dt is 0 because it is fixed. But if I want to do this derivative in a rotating frame, if I want to find it in rotating frame, then di by dt or dj by dt or dk by dt unit vectors, they are not equal to 0 in rotating frame. That is the problem. Right? So naturally, I have to put some extra term so that there is an equivalence. And what is that? You know from my last lecture, that is, if I want to derive derivative of a vector in a, let's say, dA by dt, if I want it in an inertial frame, this is equivalently dA by dt in rotating frame plus whatever the frame rotation is there cross A. This is the correction. If you add on dA by dt, evaluate a rotating frame, if I add these two, it is equivalently as if we are working in inertial frame. The derivation in the last module, I have already shown, you can see a textbook also. But as far as application point is concerned, you should now see that we have solved that riddle, that we want to operate in dA by dt inertial frame or rate of change of momentum, rate of change of angular momentum, we want to evaluate in inertial frame. But now what we are doing, we will evaluate in rotating frame because we have some advantages, and to make it equivalent to inertial frame, we'll add this omega cross A. We add these two, so it's equivalent to working in inertial frame. So I will look now towards this right hand side, and that will fulfill my desire that I still work on rotating frame, because I know there are some advantages for this specific case to work in rotating frame. It is not a generic statement. For this case, yes, it is okay, right? So now we'll apply this understanding and see what happens. I'll write here, you see inertial frame, it was m dvc by dt, right, inertial frame. So this Vc, everything was measured with respect to the inertial frame. Similarly, m was rate of change of angular momentum, again with respect to the inertial frame. But now we want to work in rotating frame equivalently. What we'll do, we'll say F equal to m dvc by dt evaluated as rotating frame plus omega cross Vc. We are using this relationship. Similarly, we'll write m as dh by dt evaluated at body frame or rotating frame, but same thing, plus omega cross h. What is omega? Omega is the angular velocity of the frame with respect to the inertial frame. Correct? What is omega? Omega is the angular velocity of the rotating frame with respect to inertial frame. Right? Now, please understand the next step. What is Vc? How I am going to expand Vc in rotating frame? In rotating frame. How I am going to express it? I wanted to work in rotating frame, so I'll write this equal to u into I plus v into j plus w into k. They are the unit vector. What are these I, j, k? I, j, k are the unit vector of the body frame. Right? Remember, di by dt, dj by dt, dk by dt is non-zero. Right? But since we are giving this correction, omega cross Vc, we can directly take the derivative in a standard form, and because the rotation part of the vector gets corrected through omega cross Vc. So what are the UVW? UVW are the component of the velocity of the frame or the body with respect to inertial frame, but resolved along body axis x, y, z. Let's understand this. If this is your airplane, this is the body axis x, the y, this is z, and here it is x earth, y earth, z earth. Then what is this Vc? Vc is the velocity of the center of mass, because we have seen from the first law that even if the forces are distributed for translational motion, you can assume whole mass is concentrated at the center of mass, at the point mass, and take the resultant of all the forces acting at different component and transfer it to the point mass and write F equal to ma. So Vc is the velocity of the center of mass with respect to Vc with respect to inertial frame. But then when I write like this, what I am saying, Vc is expressed as, which is the velocity of the body or frame respect to inertial frame, resolved along local I, j, and k unit vectors are resolved along local body axis. So you are now operating in body frame. Similarly, omega, when I write p, I plus q, j plus r, k. What is the interpretation? Omega is the angular velocity of the body or the frame. They are same because axis is fixed. Frame is fixed to the body. This is the angular velocity of the body or the frame with respect to inertial frame. However, this PQR are the component of that omega resolved along I, J, K body axis. Clear? These are two important understanding you must have. Once I have that, and once I have this relationship, I can easily find out some expression which will be very interesting. Let me erase this. Let me start with F is equal to M dVc by dt plus omega cross Vc. Let us see. Let us do some vectors. Simple elementary operation. You know Vc is nothing but Ui plus Vj plus Wk. So I can write F is equal to M d by dt of U I plus V J plus W K plus omega, you know, P I plus Q J plus R K cross U I plus V J plus W K. Right? M dVc, this is nothing but Vc, we have seen. This is nothing but W, or sorry, this is nothing but omega, and this is again Vc. Clear? Please understand, we are now operating in the body frame now. So this, when I am doing this derivative in body frame, I am not bothered about di by dt no more, because those things have been corrected here. Simply you take derivative with respect to the scalar term. So you will get F equal to M U dot plus Q W minus RV. This is one expression you will get, because this is Fx. Sorry, Fx, because you understand F is nothing but Fx I plus Fy j plus Fz k. So what are Fx, Fy, Fz? They are the component of force F resolved along body I, J, K axis system. Right? So if I do this vector operation, like simply I have to write here Fx I plus Fy j plus Fz k. Then I do this derivative, it will be u dot, this will be v dot, but j will be there, w dot, k will be there. Will you find the cross product? We will get this equation, Fx equal to that, Fy equal to m v dot plus ur minus wp and Fz equal to m w dot minus uq plus vp. You could see here, if I was operating in inertial frame, everything was inertial frame, that is, this derivative was on inertial frame, then it would be Fx equal to mu dot. This thing will not come, because that time there are no such angular velocities correction, omega cross Vc. Right? So now it is very clear, you are operating in the body frame, but same time you are maintaining the understanding that neutral application is valid only in inertial frame by using this correction. That is, what is that? Correction is dA by dt inertial frame can be equivalently operated as dA by dt body frame plus omega cross A. This understanding we have applied, and you have got Fx, Fy, Fz expression. Why we are getting all these things? Because we want to write equation of motion. But these are not perturbed equation of motion, unlike the mass spring system. Right? This is general equation of motion. We will be extracting perturbed equation of motion by doing another stage of mathematical treatment. Okay.